Hey guys, how's it going? I'm back again. Let me continue on page 172 or 180. The function directory is the most complicated. Much of it is concerned, however, with creating the full path name of the file being dealt with. Like this. If a directory slot is not currently in use because a file has been removed, the not entry is 0. And this position is skipped. Each directory also contains entries for itself called double quote point and its parent double quote double point. Clearly, there must also be skipped, or the program will run for quite a while. Although the F-side program is rather specialized, it has indicated a couple of important ideas. First, many programs are not system programs. They merely use information whose form or content is maintained by the operating system. Second, for such programs, it is crucial that the representation of the information appear only in standard header files like stat.h and dar.h, and that programs include those files instead of embedding the actual declarations in themselves. 8.7 example, a storage allocator. In chapter 5, we presented a simple-minded version of a log. The version which we will now write is an restricted. Calls to a log and free may be intermixed in any order. A log calls upon the operating system to obtain more memory as necessary. Besides being useful in their own right, these routines illustrate some of the considerations involved in writing machine-dependent code in a relatively machine-independent way, and also show a real-life application of structures, unions, and type-diff. Rather than allocating from a compiled-in fixed-sized array, a log will request space from the operating system as needed, since other activities in the program may also request space asynchronously. Asynchronously. The space a log manages may not be contiguous. Thus, its free storage is kept as a chain of free block. Each block contains a size, a pointer to the next block, and the space itself. The blocks are kept in order of increasing storage address, and the last block, highest address, points to the first. So the chain is actually a ring. When a request is made, the free list is scanned until a big enough block is found. If the block is exactly the size requested, it is unlinked from the list and returned to the user. If the block is too big, it is split and the proper amount is returned to the user while the residue resi- residue is put back on the free list. If no big enough block is found, another block is obtained from the operating system and linked into the free list. Searching them resumes. Freeing also causes a search of the free list to find the proper place to insert the block being freed. If the block being freed is adjacent to a free list block on either side, it is coalesced with it into a single bigger block. So storage does not become too fragmented. So storage does not become too fragmented. Determining adjacency is easy because the free list is maintained in storage order. One problem, which we alluded to in chapter 5, is to ensure that the storage returned by a lock is aligned properly for the objects that will be stored in it. Although machines vary, for each machine there is a most restrictive type. If the most restricted type can be stored at a particular address, all other types may be also. For example, on the IBM 360/370, the Honeywell 6000, and many other machines, any object may be stored on a boundary appropriate for a double on the PDP-11 end surfaces. A free block contains a pointer to the next block in the chain, a record of the size of the block, and then the free space itself. The control information at the beginning is called the header. To simplify alignment, all blocks are multiplies of the header size, and the header is aligned properly. This is achieved by a union that contains the desired header structure and an instance of the most restrictive alignment type. In a lock, the requested size in characters is rounded up to the proper number of header sized unions. The actual block that will be allocated contains one more unit for the header itself, and this is the value recorded in the size field of the header. The pointer returned by a lock points at the free space, not at the header itself. The variable base is used to get started. If a lock P is null, as it is at the first call of a lock, then an degenerate free list is created. It contains one block of size 0 and points to itself. In any case, the free list is then searched. The search for a free block of adequate size begins at the point where the last block was found. This strategy helps keep the list homogeneous. If a too big block is found, the tail end is returned to the user. In this way, the header of the original needs only to have its size adjusted In all cases, the pointer returned to the user is to the actual free air, which is 1 unit beyond the header. Notice that P is converted to a character pointer before being returned by a log. The function morecore obtains storage from the operating system. The details of how this is done, of course, vary from system to system. In Unix, the system entry spark returns a pointer to n more bytes of storage. The pointer satisfies all alignment restrictions. Since asking the system for memory is a comparatively expensive operation, we don't want to do that on every call to a log. So morecore rounds up the number of units requested of it to a larger value. This larger block will be chopped up as needed. The amount of scaling is a parameter that can be turned that can be tuned to need. The amount of scaling is a parameter that can be tuned as needed. Spark returns -1 if there was no space. Even if new would have been a better choice. The -1 must be converted to an int so it can be safely compared. Again, cats are heavily used, so the function is relatively immune to the details of pointer representation on different machines. Free itself is the last thing. It simply scans the free list, starting at a log P, looking for the place to insert the free block. This is either between two existing blocks or at one end of the list. In any case, if the block being freed is adjacent to either label, the adjacent blocks are combined. The only troubles are keeping the pointers pointing to the right things and the size is correct. Codes. Although storage allocation is intrinsically machine dependent. The code shown above illustrates how the machine dependencies can be controlled and confined to a very small part of the program. The use of typedef and union handles alignment, given that Spark supplies an appropriate pointer. Cats arrange that pointer conversions are made explicit and even cope with a badly designed system interface, even though the details here are related to storage allocation. The general approach is applicable to other situations as well. Exercise 8, middle score 6. The standard library function clog parenthesis n comma size returns a pointer to n objects of size. With the storage initialized to 0, write clog using a log either as a model, or as a function to be called. Exercise 8, middle score 7. A log accepts a site's request without checking its plausibility. Free believes that the block it is asked to free contains a valid size field. Improve these routines to take more pains with error checking. Exercise 8, middle score 8. Write a routine. Be free. Be free. Parenthesis p, comma n, which will free an arbitrary block at p of n characters into the free list maintained by a log in free. By using the free, a user can add a static or external array to the free list at any time. What is this? What happened? What? What is this? Appendix A. See references manual. C. References manual. Okay. 1. Introduction. The manual describes the C language and the DC PDP-11, the Honeywell 6000, and the IBM system SNASH 370, and the interdate and the interdata 8 SNASH 32. Where differences exist, it concentrates on the PDP-11, but tries to point out implementation-dependent details. With few exceptions, these dependencies follow directly from the underlying properties of the hardware. The various compilers are generally quite compatible. 2. Lexical conventions. There are 6 classes of tokens: identifiers, keywords, constants, strings, operators, and other separators. Blanks, tabs, new lines, and comments, collectively white space. As described below are ignored. Except as they serve to separate tokens. Some white space is required to separate otherwise adjacent identifiers, keywords, and constants. If the input string has been pressed into tokens up to if the input stream has been parsed into tokens up to a given character, the next token is taken to include the longest string of characters which could possibly continue a token. 2.1 comments. The characters / asterisk introduce a comment which terminates with the characters asterisk / comments do not list. 2.2 Identifiers. Names. An identifier is a sequence of letters and digits. The first character must be a letter. The underscore counts as a letter. Upper and lowercase letters are different. No more than the first 8 characters are significant, although more may be used. External identifiers, which are used by various assemblers and loaders, are more restricted. 2.3 keywords. The following identifiers are reserved for use as keywords and may not be used otherwise. In char float, keywords. This is keywords. The entry keyword is not currently implemented by any compiler but is reserved for future use. Some implementations also reserve the words Fortran and ISM. (2.4) Constants. There are several kinds of constants are listed below. Header characteristics. Header characteristics which affect sizes are summarized in 2.6. 2.4.1 Integer constants. An integer constant consisting of a sequence of digits is taken to be octal if it begins with 0, digit 0, decimal otherwise. The digits 8 and 9 have octal value 10 and 11 respectively. A sequence of digits preceded by 0 lowercase x or 0 uppercase x, digit 0, is taken to be a hexadecimal integer. The hexadecimal integer's digits. The hexadecimal digits include a lowercase a or uppercase a through lowercase f or uppercase f with values 10 through 15. A decimal constant whose value exceeds the largest signed machine integer is taken to be long. An octal or a hex constant which exceeds the largest unsigned machine integer is likewise taken to be long. 2.4.2 Explicit long constants. A decimal, octal, or hexadecimal integer constant immediately followed by L, not 1. So confused. Lowercase l or uppercase L is a long constant. As discussed below, on some machines, integer and long values may be considered identical. (2.4.3) Character constants. A character constant is a character enclosed in single quotes, as in single quote lowercase x. The value of a character constant is the numerical value of the character in the machine's character set. Certain non-graphic characters, the single quote and the backslash, may be represented according to the following table of escape sequences. The escape backslash DDD consists of the black backslash followed by 1, 2, or 3 octal digits which are taken to specify the value of the desired character. A special case of this construction is backslash 0, not followed by a digit, which indicates the character new. If the character following a backslash is not one of those specified, the backslash is ignored. 2.4.4 Floating constants. A floating constant consists of an integer part, a decimal point, a fraction part, and lowercase e or uppercase e, and a optionally assigned integer exponent. The integer and fraction parts both consist of a sequence of digits, either the integer part or the fraction part, not both, may be missing. Either the decimal point or the lowercase e and the exponent, not both, may be missing. Every floating constant is taken to be double precision. 2.5 Strings. A string is a sequence of characters surrounded by double quotes, as in double quoted ... A string has type array of characters and storage class static. See chapter 4 below. And is initialized with the given characters or strings even when written identically are distinct. The compiler places a new byte \0 at the end of each string so that programs which scan the string can find its end. In a string, the double quote character must be preceded by a \. In addition, the same escape is as described for character constants may be used. Finally, a \, and an immediately following new line are ignored. 2.6 Header characteristics. The following table summarizes certain header properties which vary from machine to machine, although this affect program portability. In practice, they are less of a problem than might be thought a priori. In practice, they are less of a problem than might be thought a priori. Look at this table. For these four machines, floating point numbers have 8-bit exponents. Three, syntax notation. In the syntax notation used in this manual, syntactic categories are indicated by italic type, and literal words and characters in bold type. Alternative categories are listed on separate lines. An optional terminal or non-terminal symbol is indicated by the subscript opt so that indicates an optional expression enclosed in braces. The syntax is summarized in whatever it is. 4. What is in the name? C bases the interpretation of an identifier upon two attributes C bases the interpretation of an identifier upon two attributes of the identifier, its storage class and its type. The storage class determines the storage class determines the storage class determines determines the storage class determines the location and lifetime of the storage associated with an identifier. The type determines the meaning of the values found in the identifier's storage. There are 4 declarable storage classes: automatic, static, external, and register. Automatic variables. Automatic variables are local to each invocation of a block and are discarded upon exit from the block. Static variables are local to a block, but retain their values upon re-entry to a block even after control has left the block. External variables excite external variable exist and retain their values throughout the execution of the entire program, and may be used for communication between functions. Even separately compiled functions, register variables are, if possible, stored in the fast registers of the machine. Like automatic variables, they are local to each block and disappear on exit from the block. C supports several fundamental types of objects. Objects declared as characters, char, are large enough to store any member of the implementation's character set, and if a genuine character from that character set is stored in a character variable, its value is equivalent to the integer code for that character. Other quantities may be stored into character variables, but the implementation is machine dependent. Up to 3 sizes of integer declared: short int, and long int are available. Long integers provide no less storage than shorter ones, but the implementation may make either short integers or long integers or both equivalent to plain integers. Plain integers have the natural size suggested by the host machine architecture. The other sizes are provided to meet special needs. Assigned integers declared and signed obey the laws of arithmetic modulo. 2 power n, where n is the number of bits in the representation. On the PDP-11, assigned long quantities are not supported. Single precision floating point and double precision floating point may be synonyms in some implementations, because objects of the foregoing types can usefully be interpreted as numbers. They will be referred to as arithmetic types. Types char and int of all sizes will collectively be called integer types. Float and double will collectively be called floating types. Besides the fundamental arithmetic types, there is a conceptually infinite class of derived types constructed from the fundamental types in the following ways. Arrays of objects of most types, functions which return objects of a given type, pointers to objects of a given type, structures containing a sequence of objects of various types, unions capable of containing any one of several objects of various types. Structures containing a sequence of objects of various types. Unions capable of containing any one of several objects of various types. In general, these methods of constructing objects can be applied recursively. 5. Objects and L values. An object is an manipulatable region of storage. An L value is an expression referring to an object. An obvious example of an L value expression is an identifier. There are operators which yield L values. For example, if uppercase E is an expression of pointer type, then asterisk uppercase E is an L value expression referring to the object to which uppercase E points. The name L value comes from the assignment expression uppercase E1 to equal uppercase E2, in which the left operand uppercase E1 may be an L value expression. The discussion of each operator below indicates whether it expects L value operands and whether it is an L value. 6. Conversions. A number of operators may, depending on their operands, cause conversions of the value of an operand from one type to another. This section explains the result to be expected from such conversions. 6.6 summarizes the conversions demanded by most ordinary operators. It will be supplemented as required by the discussion of each operator. 6.1 Characters and integers. A character or a short integer may be used wherever an integer may be used. In all cases, the value is converted to an integer. Conversion of a shorter integer to a longer always involves sign extension. Integers are signed quantities. Whether or not sign extension occurs for characters is machine dependent, but it is guaranteed that a member of the standard character set is non-negative. Of the machines treated by this manual, only the PDB-11 sign extends. On the PDB-11, character variables range in value from -128 to 127. The characters of the ASCII alphabet are all positive. A character constant specified within octal escape suffers sign extension and may appear negative. For example, single quote \377 has the value -1. When a longer integer is converted to a shorter or to HR, It is truncated on the left. Excess bits are simply discarded. 6.2 Float and double. All floating arithmetic in C is carried out in double precision. Whenever a float appears in an expression, it is named to double by 0, padding its fraction. When a double must be converted to a float, for example, by an assignment, the double is rounded before truncation to float length. 6.3 Floating and integer. Conversions of floating values to integer type tend to be rather machine dependent. In particular, the direction of truncation of negative numbers varies from machine to machine. The result is undefined if the value will not fit in the space provided. Conversions of integer values to floating type are well behaved. Some loss of precision occurs if the destination lacks sufficient bits. 6.4 Pointers and integers. An integer or long integer may be added to or subtracted from a pointer. In such a case, the first is converted as specified in the discussion of the addition operator. Two pointers to objects of the same type may be subtracted. In this case, the result is converted to an integer as specified in the discussion of the subtraction operator. 6.5 Unsigned. Whatever an assigned integer and a plain integer are combined, the plain integer is converted to unsigned and the result is unsigned. The value is the least unsigned integer congruent to the signed integer modulo 2 power word size. In a 2's complement representation, this conversion is conceptual and there is no actual change in the bit pattern. When an assigned integer is converted to long, the value of the result is the same numerically as that of the unsigned integer. Thus, the conversion amounts to padding with zeros on the left. 6.6 Arithmetic conversions. A great many operators cause conversions and yield result types in a similar way. This pattern will be called the usual arithmetic conversions. First, any operands of type char or short are converted to int, and any of type float are converted to double. Then if either operand is double and the other is converted to double, and that is the type of the result. Otherwise, if either operand is long, the other is converted to long, and that is the type of the result. Otherwise, if either operand is unsigned, the other is converted to unsigned, and that is the type of the result. Otherwise, both operands must be in, and that is the type of the result. 7. Expressions. The precedence of expression operators is the same as the order of the major subsections of this section. Highest precedence first. Thus, for example, the expressions referred to as the operands of plus are those expressions defined in 7.1 to 7.3. Within each subsection, the operators have the same precedence, left or right associativity. Associativity is specified in each subsection for the operators discussed therein. The precedence and associativity of all the expression operators is summarized in the grammar. Otherwise, the order of evaluation of expressions is undefined. In particular, the compiler considers itself free to compute sub-expressions in the order it believes is most efficient, even if the sub-expressions involve side effects. The order in which side effects take place is unspecified. The order in which side effects take place is unspecified. Expressions involving a commutative commutative and associative operator, multiply, plus, ampersand, bar, yield, may be rearranged arbitrarily even in the presence of parentheses to force a particular order of evaluation. An explicit temporary must be used. The handling of overflow and divide checking expression evaluation is machine dependent. All existing implementations of C ignore integer overflows, treatment of division by zero, and all floating point exceptions. Varies between machines and is usually adjustable by a library function. 7.1 Primary expressions. Primary expressions involving subscripting and function calls group left to right. An identifier is a primary expression, provided it has been suitably declared as discussed below. Its type is specified by its declaration. If the type of the identifier is an array of, however, then the value of the identifier expression is a pointer to the first object in the array, and the type of the expression is pointer to. Moreover, an array identifier is not an L-value expression. Likewise, an identifier which is declared function returning when used to accept the function name position of a call is converted to pointer to function returning. A constant is a primary expression. Its type may be int, long, or double, depending on its form. Character constants have type int, floating constants are double. A string is primary expression. Its type is originally array of char, but following the same rule given above for identifiers, this is modified to pointer to char, and the result is a pointer to the first character in the string. This is an exception in certain initializers. See, a parenthesized expression is a primary expression whose type and value are identical to those of the unadorned expression. The presence of parentheses does not affect whether the expression is an L value. When primary expression followed by an expression in score brackets is a primary expression. The intuitive meaning is that of a subscript. Usually, the primary expression has type pointer to. The subscript expression is int, and the type of the result is the expression. E1, E2 is identical by definition to all the clues needed to understand these notation are contained in this section together with the discussion in 7.1, 7.2, and 7.4 on identifiers, and plus respectively 14.3 below summarizes the implications. A function call is a primary expression followed by parentheses containing a possibly empty, comma-separated list of expressions which constitute the actual argument to the function. The primary expression must be of type function returning, and the result of the function call is of type. As indicated below, a hitherto unseen identifier followed immediately by a left parenthesis is contextually declared to represent a function returning an integer. Thus, in the most common case, integer-valued functions need not be declared. Any extra arguments of type float are converted to double before the call. Any of type char or short are converted to int, and as usual, array names are converted to pointers. No other conversions are performed automatically. In particular, the compiler does not compare the types of actual arguments with those of formal arguments. If conversion is needed, usercast see 7.2, 8.7. In preparing for the call to a function, a copy is made of each actual parameter. Thus, all argument passing in C is strictly by value. A function may change the values of its formal parameters, but these changes cannot affect the values of the actual parameters. On the other hand, it is possible to pass a pointer on the understanding that the function may change the value of the object to which the pointer points. An array name is a pointer expression. The order of evaluation of arguments is defined by the language. Take note that the various compilers differ. Recursive calls to any function are permitted. A primary expression followed by a dot followed by an identifier is an expression. The first expression must be an L value naming a structure or a union, and the identifier must name a member of the structure or a union. The result is an L value referring to the named member of the structure or a union. A primary expression followed by an arrow built from a midscore and a right angle bracket. Followed by an identifier is an expression. The first expression must be a pointer to a structure or a union, and the identifier must name a member of that structure or union. The result is an L value referring to the named member of the structure or union to which the pointer expression points. Thus, the expression E1 arrow mouse is the same as like this. Structures and unions are discussed in 8.5. The rules given here for the use of structures and unions are not enforced strictly. In order to allow an escape from the typing mechanism, see 14.1. 7.2 Unary operators. Expressions with unary operators group right to left. The unary asterisk, the unary multiply operator means indirection. The expression must be a pointer, and the result is an L value referring to the object to which the expression points. If the type of the expression is pointer to, the type of the result is. The result of the unary ampersand operator is a pointer to the object referred to by the L value. If the type of the L value is, the type of the result is pointer to. The result of the unary minus operator is the negative of its operand. The usual arithmetic conversions are performed. The negative of an assigned quantity is computed by subtracting its value from 2 power n, where n is the number of bits in an int, and there is no unary plus operator. Why? Why there is no unary plus operator? I just want to know. The result of the logical negation operator classic is 1 if the value of its operand is 0, 0 if the value of its operand is non-zero. The type of the result is int. It is applicable to any arithmetic type or to pointers. The yield operators yields the one's complement of its operand. The usual arithmetic conversions are performed. The type of the operand must be integer. The object referred to by the L value operand of prefix plus plus is incremented. The value is the new value of the operand, but it is not an L value. The expression plus plus lowercase x is equivalent to lowercase x plus equal 1. Since the discussions of addition 7.4 and assignment operators 7.14 for information on conversions, the L value operand of prefix minus minus is decremented analogously to the prefix plus plus operator. When postfix plus plus is applied to an L value, the result is the value of the object referred by the L value. After the result is noted, the object is incremented in the same manner as for the prefix plus plus operator. The type of the result is the same as the type of the L value expression. When postfix is applied to an L value, the result is the value of the object referred to by the L value. After the result is noted, the object is decremented in the manner as for the prefix minus minus operator. The type of the result is the same as the type of the L value expression. An expression preceded by the parenthesized name of a data type causes conversion of the value of the expression to the name type. This construction is called a cast. Type names are described in 8.7. The size of operator is the size in bytes of its operand. A byte is undefined by the language except in terms of the value of size of. However, in all existing implementations, a byte is the space required to hold a char. When applied to an array, the result is the total number of bytes in the array. The size is determined from the declarations of the object in the expression. The expression is semantically an integer constant and may be used anywhere a constant is required. Its major use is in communication with routines like storage, allocator, and exponential systems. The size of operator may also be applied to the parenthesized type name. In that case, it is the size embodies of an object of the indicated type. The construction size of is taken to be a unit, so the expression size of minus 2 is the same as like this. 7.3 Multiplicative operators. The multiplicative operators asterisk, star or slash, and percent group left to right. The usual arithmetic conversions are performed. The binary asterisk operator indicates multiplication. The asterisk operator is associative, and expressions with several multiplications at the same level may be rearranged by the compiler. The binary slash operator indicates division. When positive integers are divided, truncation is toward 0. But the form of truncation is machine dependent if either operand is negative. On all machines covered by this manual, the remainder has the same sign as the dividend. It is always true that parenthesis a slash b multiply b plus a percent b is equal to a if b is not 0. The binary percent operator is the remainder from the division of the first expression by the second. The usual arithmetic conversions are performed. The operands must not be float. 7.4 Additive operators. The additive operators plus and minus group left to right. The usual arithmetic conversions are performed. There are some additional type possibilities for each operator. The result of the plus operator is the sum of the operands, a pointer to an object in an array, and a value of an integer type may be added. The latter is in all cases converted to an address offset by multiplying it by the length of the object to which the pointer points. The result is a pointer of the same type as the original pointer and which points to another object in the same array, appropriately offset from the original object. Thus, if P is a pointer to an object in an array, the expression P plus 1 is a pointer to the next object in the array. No further type combinations are allowed for pointers. The plus operator is associative, and expressions with several additions at the same level may be rearranged by the compiler. The result of the minus operator is the difference of the operands. The usual arithmetic conversions are performed. Additionally, a value of any integer type may be subtracted from the pointer, and then the same conversions as for addition apply. If two pointers to objects of the same type are subtracted, the result is converted by division by the length of the object to an end representing the number of objects separating to the pointed to objects. This conversion will, in general, give unexpected results unless the pointers point to objects in the same array, since pointers even to objects of the same type do not necessarily differ by a multiple of the object names. 7.5 Shift operators. The shift operators, left shift and right shift, group left to right, both perform the usual arithmetic conversions on their operands, each of which must be integer. Then the right operand is converted to int. The type of the result is that of the left operand. The result is undefined if the right operand is negative or greater than or equal to the length of the object in bits. The value of E1 left shift E2 is E1 interpreted as a bit pattern. Left shifted E2 bits. Vacated bits are zero field. The value of E1 right shift is E1 right shifted E2 bit positions. The right shift is guaranteed to be logical zero field if E1 is unsigned. Otherwise, it may be and its own P2P11 arithmetic field by a copy of the sign bit. 7.6 Relational operators. The relational operators group left to right, but this fact is not very useful. A less than B less than C does not mean what it seems to. The operators less than, greater than, less than or equal to, and greater than or equal to all yield 0 if the specified relation is false, and 1 if it is true. The type of the result is int. The usual arithmetic conversions are performed. Two pointers may be compared. The result depends on the relative locations in the address space of the pointed to objects. Pointer comparison is possible only when the pointers point to objects in the same array. Equality operators, the equal and the exclusive equal operators are exactly analogous to the relational operators except for their lower precedence. Thus, A less than B equal C less than D is 1. Whatever A less than B and E and C less than D have the same truth value. A pointer may be compared to an integer, but the result is machine dependent. Unless the integer is a constant 0, a pointer to which 0 has been assigned to guaranteed not to point to any object, and it will appear to be equal to 0. In conventional usage, such a pointer is considered to be null. 7.8 Bitwise AND operator. The ampersand operator is associative, and expressions involving ampersand may be rearranged. The usual arithmetic conversions are performed. The result is the bitwise AND function of the operands. The operator applies only the integer operands. 7.9 Bitwise exclusive OR operator. What is this? Symbolic? I don't know. The operator is associative, and expressions involving may be rearranged. The usual arithmetic conversions are performed. The result is the bitwise exclusive or functional of the operands. The operator applies only to integer operands. 7.10 Bitwise inclusive OR operator. The bar operator is associative, and expressions involving bar may be rearranged. The usual arithmetic conversions are performed. The result is the bitwise inclusive. The result is bitwise 7.10 bitwise inclusive or operator. And the bar operator is associative, and expressions involving bar may be rearranged. The usual arithmetic conversions are performed. The result is a bitwise inclusive or function of its operands. The operator applies only to integer operands. 7.11 Logical and operator. The ampersand operator groups left to right. It returns 1 if both its operands are non-zero. 0 otherwise, and like ampersand guarantees left to right evaluation. Moreover, the second operand is not evaluated even if the first operand is 0. The operands need not have the same type, but each must have one of the fundamental types or be a pointer. The result is always int. 7.12 Logical or operators. The bar operator groups left to right. It returns 1 if either of its operand is non-zero, and 0 otherwise. Unlike bar guarantees left to right evaluation. Moreover, the second operand is not evaluated if the value of the first operand is non-zero. The operands need not have the same type, but each must have one of the fundamental types or be a pointer. The result is always int. 7.13 Conditional operator. Conditional expressions group right to left. The first expression is evaluated, and if it is non-zero, the result is the value of the second expression, otherwise that of third expression. If possible, the usual arithmetic conversions are performed to bring the second and the third expressions to a common type. Otherwise, if both are pointers of the same type, the result has this common type. Otherwise, one must be a pointer and the other the constant 0. And the result has the type of the pointer. Only one of the second and third expressions is evaluated. Question, query, or 7.14 Assignment operators. There are a number of assignment operators, all of which group right to left. All require an L value as their left operand. And the type of an assignment expression is that of its left operand. The value is the value stored in the left operand after the assignment has taken place. The two parts of a compound assignment operator are separate tokens. In the simple assignment with equal, the value of the expression replaces that of the object referred to by the L value. If both operands have arithmetic type, the right operand is converted to the type of the left preparatory. The left preparatory. The right operand is converted to the type of the left preparatory to the assignment. The behavior of an expression of the form E1 OP equal E2 may be inferred by taking it as equivalent to E1 equal E1 OP parentheses E2. However, E1 is evaluated only once in +1. In plus equal or minus equal, the left operand may be a pointer, in which case the integer right operand is converted as explained In 7.4, all right operands and all long pointer left operands must have arithmetic type. Okay, guys. I need a break. See ya.